procedure that we recorded, so we'll do that now, and then I'll introduce you. I'll speak a few words in Portuguese for the benefit of the Portuguese speaking people, and then you can start after me. Is it okay?
Yes, that will be fine. Thank you very much.
Ok. Antônio, então, pode botar aí para transmitir para o YouTube.
Estamos ao vivo.
Já posso começar?
Sim.
Ah, ok. Muito obrigado, Antônio. Então, hoje, no dia 13 de agosto, a gente tem o prazer de receber o professor Frederick Gray, da Regis University. Ele faz parte da colaboração do experimento do Muon G-2 do Fermilab, que apresentou resultados interessantíssimos durante esse ano. Vocês estão vendo aí já a foto do experimento. E a colaboração e o professor Fred foram muito gentis em nos dar um seminário especial só para nós aqui no programa, onde a gente vai poder entrar mais nos detalhes dos resultados e fazer perguntas, tá? O seminário vai ser em inglês, e então se vocês tiverem perguntas em português, vocês podem fazer, eu vou traduzir elas para inglês para o professor Fred. Também vocês podem colocar perguntas ali no chat, e então eu vou agora apresentar ele em inglês. Okay, so now we have the pleasure to have Professor Fred here from Regis University. He's going to talk about these nice and interesting results, very meaningful and recent. We have the pleasure to have a special presentation just for our grad school. And that was very nice. Thank you very much, Fred, and thanks to the collaboration for giving us such an opportunity. So, do you want to take questions while you are presenting, or do you want the questions towards the end?
I would be very glad to take questions during the presentation. I think that it's, for me, of course, always much easier than trying to remember until the end what my question was.
Right. So if
yes,
you want to make some stops, like any questions so far, then maybe people will ask questions, ok? Então ele falou que vocês podem fazer perguntas durante o seminário, tá? E aí ele vai responder durante o seminário, não precisa esperar até o final. So, okay, thank you very much for being with us this morning, Fred, and please go ahead, show us what you got.
Oh, thank you very much, and thank you for the invitation to speak to your group. I really wish that I could visit in person. You all are in a beautiful place, and I would love to meet you all in person someday, and I hope that becomes possible again soon. But yeah, for now, I'm glad to be able to talk with you. I'm currently at Fermilab, but I teach at Regis University in Denver in Colorado in the United States. And so let's see. Let me go to the next slide here. So ultimately, particle physics addresses many of the same questions as, for example, astronomy and astrophysics. You know, people have been looking out into the sky for a very long time to ask sort of the big questions. So what is the universe all made of? And then really, you know, the other big question, how did we as people, but as atoms, get here? And so the answer in particle physics, as we know it now, is the standard model of particle physics. That it answers the big question, what is it all made of? What is everything made of? And the standard model, you know, says that there are 3 generations of quarks. So there are up and down quarks that, for example, protons and neutrons are built from, but then there are heavier flavors of quarks, charm and strange and top and bottom quarks. And so all baryons, like the proton and the neutron, and mesons, like the pion, are built from quarks and their antiparticles, the antiquarks. So in addition, the standard model says that there are 3 generations of leptons, just like there are 3 generations of quarks. So there's an electron generation, a muon, which we're going to use as the probe, the test particle in our experiment, and the tau particle. And each of those has a neutrino that is associated with it. So in addition to these matter particles, there are force carrier particles. So we can see the photon as being the particle that carries the electromagnetic interaction. And we can see the W and the Z boson particles as the particles that carry the weak nuclear interaction, and the gluon as the particle that carries the strong nuclear interaction. And so those bosons are called bosons because they have integer spin, generally spin 1, whereas the others, the quarks and the leptons, they are fermions, so they have spin 1/2, half integer spin. Then the last piece of the standard model to be discovered was the Higgs boson. And the Higgs boson, by its couplings to all of these other fundamental particles, gives them mass. So that's the big picture, and it explains almost everything that was ever observed so far in particle physics experiments, with only a very few exceptions. Our experiment that I will tell you about is one of those exceptions that is not fully explained now by the standard model of particle physics. There have also been some recent measurements where B mesons were seen to decay differently into muons compared to their decay into electrons. And that is not fully explained by the standard model. In fact, all of the discrepancies that we see now with the standard model somehow involve muons. The standard model does not have a natural way to explain the asymmetry between matter and antimatter, between particles and their antiparticles. Because we are made of matter and not of antimatter, this is really the big question of how did we get here? How is it that we can exist? How is it that we can be made of matter? Why did all the matter and all the antimatter not annihilate with each other in the early universe? And the standard model, unfortunately, does not explain anything about dark matter. So astronomers tell us that there is 5.5 times as much dark matter as normal matter in the universe. And they also tell us about dark energy, and there's even, a larger density of dark energy in the universe than of dark matter. And the standard model really hardly even has the right kinds of words to begin to talk about dark energy. And it doesn't explain the hierarchy problem, which you could see in 2 ways. Why is gravity so weak compared to the other forces? Or why is the Higgs mass so small compared to the very large universal scale of the Planck scale, a very high energy scale? So to try to address this, we believe that there must be some new physics beyond the standard model, but direct searches for that new physics have not yet uncovered it. So instead of looking for producing the new kinds of particles directly, for example, in experiments like ours, we are searching for indirect hints in the form of the subtle effects of virtual particles on the muon that will be our test particle. So we all experience muons all the time in the form of cosmic rays. And so in our experiment at Fermilab, we use those muons as probes to test the standard model. but the muons that we all are constantly experiencing the effects of come from the sky. So primary cosmic rays, like protons or helium nuclei, hit the upper atmosphere, and when they do, they break apart nuclei in the upper atmosphere. They even break apart the protons and the neutrons within those nuclei to produce showers of pions mostly, but also some kaons, maybe some other kinds of particles. Then those pions, after coming down a little, they decay into muons. And so the muons are the particles that reach down to the surface of the Earth. So, you know, down at the elevation where I live in Denver, it's almost all muons. If you go up to the top of the mountains, this is Pikes Peak in Colorado, you can still find a few of the pions up there. But yeah, reaching lower elevations, like where probably all of us are now, we only have muons. And so the muon mass is about 220 times the mass of the electron. So, you know, the electron has a mass of about half an MeV over c squared. And yeah, unlike the electron, the muon is an unstable particle that decays with an average lifetime of a little more than 2 microseconds. And in our experiment at Fermilab, we take muons and we inject them initially with their spins nearly parallel to their momentum vectors. Over time, we watch the spin rotate a little bit faster than the momentum rotates, and it's that anomalous precession frequency, that is how much faster the spin rotates than the momentum, that we measure. And that frequency is proportional to G-2, so that's the name of the experiment, right? So yeah, it's proportional to G-2 divided by the magnetic field. So the stronger the magnetic field, the faster the spin will precess. The larger G-2 is, the faster the spin will precess. What is G? Well, G is a way of writing the muon's magnetic moment. So it's a way of writing the magnetic moment in units that have no units, right? So as a pure number. It's a way of expressing the magnetic moment so that it is the constant that sort of multiplies the angular momentum of the muon, its spin angular momentum, and some other constants to give the magnetic moment of the muon. So again, we store a polarized beam of muons, that is all their spins pointing the same direction, in a uniform magnetic field, same magnetic field everywhere that the muons see, and we observe the spin precession. So, let's see. Yes, I advanced one slide too far. Okay. The basic process of the muon interacting with the magnetic field is seen in this Feynman diagram. So remember that the photon is the carrier of the electromagnetic interaction. And here you see at this point, at this vertex, the interaction between a muon and the photon that carries that magnetic field from our large magnet. You see the muon interacting with it, having its spin rotated by that interaction, and then, you know, the muon goes out again. So in these Feynman diagrams, space is on the vertical axis and time proceeds along the horizontal axis. So this is sort of the bare magnetic moment interaction of a fundamental particle, of the muon alone. If we add indirect interactions in here, so where the muon does not only interact directly with the magnetic field, but also indirectly through an intermediate state, that contributes an anomalous part to the magnetic moment. So the bare magnetic moment would give G equals 2, which would mean that the spin does not precess. But then there is an anomalous part that causes the spin to turn slightly faster than the momentum that comes from the insertion of virtual particles into these interactions. So G is a little bit more than 2. So the anomalous part is sort of 0.001. So it's a small contribution, all from virtual particles. Here is a cartoon. It shows the muon not alone, but surrounded by this cloud of all kinds of virtual particles. Here's an electron in this cartoon looking at the muon and saying, I don't even know who you are anymore, because the muon is surrounded by this cloud of particles that come into existence and disappear again, each of them affecting the muon's magnetic moment in a measurable way, changing its value. So again, the muon alone would have G equal 2, but because of this cloud of virtual particles, G is not equal to 2. So I think this may be a good time to pause now that we've talked about sort of the very basic concept of the experiment. What questions do you all have at this time already?
Então, se vocês tiverem perguntas, eu posso traduzir.
I see that people are typing. Right, yes, could I explain more about the virtual particles? So I will move on in my talk, and I'll tell you about the simplest kind of virtual particle is simply an additional photon that is momentarily created, that only lives for a tiny amount of time, and that then is annihilated again. So actually, let me show that on the next, let me go a few slides forward there. Okay, so this is the simplest kind of virtual particle, where the muon radiates a single photon, and in this process, its spin is slightly rotated. That's in the process of interacting with the magnetic field that is applied from our main magnet. And then that virtual photon is reabsorbed. So this single process, that accounts for 99.6% of all of the virtual particles. But not only photons can appear in diagrams like this. So the photon could then in turn create a particle-antiparticle pair. So it could create, for example, an electron and a positron pair, or a quark and an antiquark. And all of those are possible. So every kind of matter can, in principle, appear in diagrams like this, where these virtual particles, they are allowed by the Heisenberg uncertainty principle, because the total energy of the system experiences quantum fluctuations. The total energy of the system is not a perfectly fixed quantity, but there is a Heisenberg relation delta E times delta T is greater than or on the order of h bar, Planck's constant, divided by 2. And so that allows for these fluctuations in energy that corresponds to fluctuation in the total amount of mass. And so those are the virtual particles that they certainly exist and can be measured during the time that they exist. They have an indirect effect on the muon, but they are not sort of permanently in existence. Does that, I hope, answer your question? Yes, yes. So that is correct. The experiment does try to measure the sum of all of these contributions. So to put it simply, the standard model makes a very precise prediction of the anomalous magnetic moment of the muon based on all of the known particles and the ways that they interact. And now our collaboration at Fermilab has made a very precise experimental measurement of that anomalous magnetic moment, so including all of those clouds. And we compare the prediction of the standard model with our experimental value, and to the extent that they do not agree, that difference could be caused by new particles and interactions that are not yet discovered. Okay, thank you, thank you. I'm just watching questions being typed. Okay, I'll ask maybe if there are any more questions, or if not, there will be more opportunities later.
Yes, I think you could go on. Can I put the link you sent us on the chat here so people can download automatically?
Oh, yes, absolutely. I believe that link should work for everyone to be able to download these slides.
Yeah, just tried it, it worked.
Okay, good.
Thank you.
Great. So often when we give these presentations, we save the result for the end. But by now, I think our result is fairly famous, right? Everyone sort of knows how this turned out. So I won't try to keep it a secret until the end. I will show you already now what we found and announced at the beginning of April of this year. So the standard model prediction was here, this green band, and there had been a previous result from an experiment at Brookhaven National Laboratory that's located near New York City in out on Long Island. And I worked on that experiment as well, I should say. That was where I got my PhD, was from this this measurement here. So this data point ended up more than 3 standard deviations away from the standard model. And so there has been a discrepancy for a long time now. We last took data at Brookhaven in the year 2001. And so since then, there has been this large unexplained discrepancy. So now at Fermilab, we measured again, and in our new experiment on its own, that ended up 3.3 standard deviations higher than the standard model. So again, not very compatible with the standard model, but very compatible with the Brookhaven measurement. So, you know, this was very happy for me, you know, having worked on both. Probably this wasn't a mistake. Probably this is really what nature is telling us in this experiment. So when you average those two results together to get the world average appropriately weighted by the uncertainties of these results, that gives you this point here, that's the purple band. And it is 4.2 standard deviations above the prediction of the standard model, where there we are taking into account both the uncertainty of the standard model prediction, which is this result. It's known with a precision of 368 parts per billion. And then we compare that now with the measurement you know, that's combined between Brookhaven and Fermilab. And that's known now to a very similar precision of about 350 parts per billion. And it's in that difference between the average of the experiments and the standard model theoretical prediction that we find this discrepancy that is large, although it does not yet reach 5 standard deviations, which is where the community in particle physics says that you're allowed to use the word discovery. So we're not yet saying that this is a discovery, but we're saying that we have new and stronger evidence for a discrepancy between the experiment and the theory. So as I said, in the theory, in the theoretical prediction of the standard model, the simplest part of it comes from the radiation of one virtual photon and its reabsorption by the muon. And so this diagram, you can calculate it. It's in a quantum field theory textbook. You learn how to calculate this. It's the Schwinger term, alpha divided by 2 pi, where alpha is about 1 over 137 is the result. And so that is 0.00116. And so that is 99.6% of the entire anomalous magnetic moment of the muon comes from this diagram. And this term is the same for the electron and for the muon. Both of them have nearly the same anomalous magnetic moment because the photon is massless. So if you put in massive particles in your diagram, particles that have a non-zero mass, then their contributions scale as the square of the mass. So that means that the muon will be more sensitive to contributions that involve massive particles, like some that we'll look at next, even though it's the same calculation for massless particles like the photon. So, you know, that was an example of the one and only diagram that contains only one loop. These are some of the diagrams that contain 2 vision lattice calculation that doesn't quite agree. But at this point, they recommend to use these data-driven evaluations. This will be a discussion for the future, because as you see, the lattice calculation is much closer to the experimental result. It's much closer. The standard model and our result, for example, are much closer together if you use this lattice calculation than if you do it the traditional way. But the discrepancy has to be understood. So again, as I say, the theory community, really the world's theory community, would recommend this as the most reliable standard model prediction for now, but we have to watch this story for the future. Okay, and I should say that there is one other hadronic contribution to the prediction, and so it's from this diagram where 3 photons are exchanged with the muon, and then there's the interaction with the applied magnetic field. It's called light by light scattering, and so now I think there are many approaches that are in good agreement for it. So this is maybe no longer such a concern. The theory initiative recommends this value for that part. So 2 approaches with the lattice and with the data-driven relations are in good agreement with each other and with the historical ways of doing this calculation. Okay, so now, having seen our result and the standard model, if there is a discrepancy, if it's not just that there's a problem with either the calculation or the experiment, then there could be new physics beyond the standard model. So it could be supersymmetry, which would say that for every boson, every integer spin particle that we know, there's a new fermion, a new half-integer spin particle. And for every fermion that we know, there is a new boson. And at the Large Hadron Collider at CERN, they have been searching directly for these new particles, and they haven't seen any. So that sets some very strong constraints that they have not been seen at the LHC. But there are still some possible scenarios where supersymmetry is allowed. still, the fact that supersymmetry has not appeared directly at the LHC makes people look at other models. So, for example, at leptoquarks, particles that can both couple to quarks and to leptons. Like at this point here, this phi particle couples to both the lepton and the quark. No particle in the standard model does that directly. So could that be one hypothesis? Or could there be additional gauge bosons, like this Z prime, that appears just like the photon and just like the Z did in possible diagrams? That's certainly one category of models that people investigate. Our paper was published in April, and already yesterday it had been cited 238 times. And so more than 50 of those have already themselves been published. And so the majority of these papers that cite our result are evaluating some model in the context of our new result. So there are many theoretical ideas for what might explain the discrepancy between the standard model and our experimental measurement. And so these are just a small selection of those possible models. So, all right, that's where I wanted to stop talking about theory, maybe, and switch over to talking about the experiment. So, does anyone have any questions about the theory?
Well, actually, I have one.
Great, please.
And okay. So when you showed that world average, can you go back to that page, please?
Yes, absolutely.
Yes. So no, the next. Yeah. Well.
Let's see. Is it here? Sorry, it's probably
with the lattice data as well. Lattice results, yes.
Is it okay? I'm sorry. There, this picture.
Yeah, when you show that in the standard model, do you include the lattice data in this standard model prediction or not?
No, at present, this the standard model contribution. Let's see, the hadronic vacuum polarization comes entirely from data-driven evaluations. The lattice results are not yet included in the recommended value for the standard model from the theory initiative. The one place where the lattice is used in this standard model value is in the hadronic light-by-light scattering contribution. There, the lattice results and the data-driven evaluations are considered equally reliable, and they are combined.
Okay, I see. Okay, but that's like 1/10 of the hadronic contribution, right?
That's right. So it's a tiny perturbation to this. So you are absolutely right that I think the big story that we're all watching is how the lattice calculations in the hadronic vacuum polarization, how they are accepted or not, how the discrepancy between them and the data-driven evaluation is resolved. Because there, not only do we have to say that they give different results, but we have to explain why. And the theory community is certainly working hard now on trying to do cross-checks of portions of the calculation in order to understand the source of the difference between them.
Great, thank you. There is another question on the chat.
Right, I see. So why do hadronic and electroweak contributions contribute less? So for the electroweak, it's easy to see because it's in the name weak. So the couplings for the weak interaction are really small. And for the hadronic contribution, there it's, I believe easiest to see that the masses are large. And so it's sort of suppressed by the by the masses of the hadronic particles compared with the very light particles, like, for example, the electron, or the massless particle like the photon. I think that's the simplest way of approaching that. So let's see. All right, if we go ahead, let me find where the experiment begins. Okay, so the simplest experiment that we could do would use cosmic ray muons and stop them. So this isn't how we did our experiment, but let's just think about it. Positive muons would always be produced with their spin oriented opposite to the momentum. So when a positive pion decays into a positive muon and a neutrino, then because the pion has zero spin, in order to conserve angular momentum, if the neutrino is all left-handed, and as far as we know, all neutrinos are left-handed, then the muon also has to be left-handed. So it has to have its spin opposite to its momentum, so that the total spin of the two particles adds up to zero, like the spin of the pion. So we make easily polarized muons. And now, after the muons stop in the experiment, their spins remain oriented essentially the same direction. And in an applied magnetic field, their spin would rotate. So it would rotate at a speed that's proportional to g and to the applied magnetic field. So it would precess around sort of like a top, right? Like a toy top that you spin. Now we have that precession, that top. So the spin vector is precessing around. Again, because of the parity violation in the weak interaction, the positron produced when the muon decays tends to preferentially follow the direction of the muon spin at the moment of decay. So that means that when the spin was pointing towards a detector, then the positrons will tend to go towards the detector. And when the spin was pointing away from a detector, then the positrons will tend to go away from the detector. And this experiment was done a long time ago. So this is a paper from 1974. This is something you could probably easily set up in your own laboratory. So if you turn your magnet off, you just see the exponential decay of the muons. If you look at the number of positrons that you count as a function of the time after you sent in the muon. But now, when you turn the magnet on, you see that the rate of positrons detected goes up and down, and up and down, and up and down. So it's modulated now at a rate that's proportional to g. So at a rate that's proportional to the rate of this spin precession, so the rate at which the muon spin vector rotates around the applied magnetic field. Of course, let's see, went too far. Okay, yeah, we don't use cosmic ray muons and we don't stop them. So we measure the muons in flight as they travel. And so, you know, for muons at rest, this was the formula for how fast their spin rotated. But when they're in flight, you have to take into account the effects of relativity, which adds this additional term. You have to subtract the frequency at which they make orbits around the storage ring. So they're going around in circles, and we have to subtract the frequency of their circular orbits. And so we do that, and what we're left with is a difference between the frequency of the muon spin precession and the cyclotron frequency, the frequency of orbits, that's proportional not to g, but to g over 2 minus 1. So it's proportional only to the anomalous part. So we measure, by measuring muons in flight, the 0.001 and not the 2. So we gain 3 more digits of precision in our experimental measurement by measuring them in flight. And I should say that in this calculation, I've ignored electric fields, and I've assumed that all the motion is in a horizontal plane. That, yeah, this is a simplified formula, but it gives the insight that shows why our experiment is sensitive to A, the anomalous part, and not to the whole thing that includes the 2. So the muons that we get are not from cosmic rays. They are from a proton accelerator at Fermilab. So we use protons with an energy of 8 GeV from the booster, which is this accelerator down here at Fermilab. They're sent up into this recycler ring, and they go around there. Every 1.33 seconds, we get 16 bunches of muons. So those are kicked out of this recycler ring and onto a target that represents, you know, the place where the protons strike a metal target and then pions are produced, just like cosmic rays striking the upper atmosphere produce pions. But then those pions have a chance to decay over 3 times around this delivery ring. So that gives them more than 2 kilometers of path length from the target to our experimental area here. And we're able, by sending them around this delivery ring, to let the muons get a little bit ahead, to move a little bit faster than the protons, so that we can use just the muons and kick out the protons and get a beam of basically only muons with a few positrons mixed in. It's about 250 nanoseconds long. And again, we get 16 of those short bunches every 1.33 seconds while we're running. And I'm waiting for the slide to change. Okay, and we bring those in, and they come down this beam line where they are focused into our storage ring. So they come in. This is the magnet before the white insulation was put on top. So yeah, they come in back here, and they go around and around and around, except that because they are in a uniform magnetic field, they make circular orbits. So if we did nothing else, they would make one turn, and then they would strike their injection point. They would come right back to where they were inserted and hit the wall there. So we don't want that. So we have a kicker that kicks them onto the correct orbit. After that, they are able to circulate for many, many turns. So the radius of this ring is a little more than 7 meters. The magnetic field is 1.45 Tesla. The muons are at a magic momentum of 3.1 GeV over c. It takes them 149 nanoseconds, 149 billionths of a second, to go around one loop. Their dilated lifetime, so taking into account special relativity, is 64.4 microseconds. Remember, their undilated lifetime was more like 2 microseconds. So they live a lot longer, and we can observe them for a lot longer because of relativistic time dilation. And their spin rotates around 1 G-2 cycle every 4 or so microseconds. So those are the basic parameters, the basic scales of this experiment. Taking a second to load. Okay, the magnet was built on the experiment that was done at Brookhaven, which actually was inspired by experiments that were done at CERN a long time ago. So Brookhaven is here, and Fermilab is here, and there you can see the coils of the magnet going on a barge through St. Louis in the United States, and So we reused the magnet, we reused the vacuum chambers, we reused the inflector, which is another magnet that cancels out the field of the main magnet. But most everything else in the experiment is new, and most all of the people are new. So there are only 11 out of the 190 of us working on the experiment at Fermilab who had previously worked on the experiment at Brookhaven. So there are a lot of people, especially younger people, with good new ideas to bring. So yeah, the magnet was delivered out of the box. It was about an order of magnitude worse than it was when it left Brookhaven, but yeah, some very smart colleagues found ways of shimming the magnetic field here, for example, with iron foils that they added very strategically based on measurements that they did. Yeah, so these iron foils really even out the magnetic field and make it more uniform as you go around the magnet. So we ended up with this red curve of magnetic field versus azimuth, versus position around the ring, that's much more uniform than the same magnet that you see in cross-section here was at Fermilab. So first they had to adjust the positioning of the poles. Then they had to adjust the wedges and the top hats. So they moved those around to equalize the field. And then their final move was to place these laminations with iron foils to get the final uniformity. They measure the magnetic field with nuclear magnetic resonance, NMR. So they watch proton spins precess in the magnetic field. And so that is the basic technique that we use. You see the oscillations of protons in either water or another substance in the coil here. And so what we measure is really the muon spin precession frequency divided by the proton spin precession frequency with some other constants needed that other people have measured to get to our final result. So we ultimately reference our magnetic field to a water probe. And so we make measurements with a trolley that contains many separate probes that actually contain petroleum jelly. They contain, Vaseline. But we calibrate them against a water probe that's made very spherically that is well understood. So there is an absolute knowledge of the magnetic field and its relationship to the NMR frequency in spherical water samples. We also monitor with 378 fixed probes that are placed around the experiment. So, right. I mentioned that we have an inflector magnet that cancels out the field of the main magnet to give zero field so the particles move straight ahead. And then we need a kicker to kick onto the right orbit. So this is a picture of our kicker pulse together with the shape, the profile of the muons as they come in. So we time when we fire the kicker magnet to match when the muons come in. And we make a very quick pulse with an unterminated transmission line, with what's called a Bloom line network. And then we focus the beam with high voltages that are applied, positive high voltage on the vertical plates, negative high voltage on the horizontal plates, so that this is vertically focusing. It pushes positive charges towards the center. Magnetic fields are naturally horizontal focusing, so we just have to not defocus too much horizontally. The reason that magnetic fields are naturally horizontally focusing is that on a circular orbit, if you're a little bit too far to the outside on one side, you're going to be a little bit too far to the inside on the other side of the ring, halfway around. So, and we focus with electric fields because we choose a beam momentum where the spin does not rotate in response to the electric field. So where this term is 0, so that's why we use muons that have a momentum of 3.09 GeV over c. So that allows us to use large electric fields to focus the beam. Okay, so here I have a video that this may work to show you what a muon sees going around the ring. Let's see, does this work for you all? So here we see the inflector. So this is where the muons come in, off to the left side. Now we're going faster to get to our next place, but there are the quadrupole plates. And we're inside the quadrupole plates being focused. Okay, now here is the kicker. So some current flows down one side and back along the other side to produce a vertical field while the kicker is firing. There's another kicker. We have 3 kickers. And then we're approaching another set of quadrupole plates. Okay, I think this gives maybe a good enough idea of what a muon would see flying around. Okay, when the muons decay, they decay into positrons. So we observe the positrons in calorimeter detectors that are placed just on the side of the vacuum chamber. So the high energy particles, the high energy positrons, tend to follow the muon spin direction, just like we said for the cosmic rays. And so what we see is that the average energy of the positrons goes up and down as the spin rotates. So when the spin points towards the detector, we see more higher energy particles, and we see more lower energy particles when the spin is pointing away. So the energy spectrum is modulated at the spin precession frequency that we're measuring. So we have 24 of these calorimeters that measure the positron energies, and they're located around that inner circumference of the storage ring. And so those 24 calorimeters, each of them is a stack of lead fluoride crystals that produce Cherenkov light. So it's a 9x6 grid of crystals. We have silicon photomultipliers that take the light that's produced, the Cherenkov light, and make electrical signals. We continuously sample those signals, and we use a graphics processing unit cluster to process the recorded waveforms. So we record events that look like this. So this is sort of light intensity inverted versus time. We record those and we process them in computers using the graphics processors to extract the energies and times. So we can even take events where multiple positrons hit the detector, and we can resolve those into the separate positron events. And so you can see that, you know, by the time 2 positrons hit a little less than 10 nanoseconds apart, already they're very easy to resolve. And we have to deal with that because higher energy positrons fly for a longer time. So they come from a different phase in the oscillation of the spin. So if we counted 2 lower energy positrons as one higher energy one, we get the phase wrong. And because there are more of those events earlier, when there are more particles in the ring before they've decayed, then the phase will change versus time. And a time-dependent phase is the same as a shift in the frequency. So we have to correct for this pileup of multiple events before we fit the data. We also have to correct for the fact that the silicon photomultipliers aren't perfect. Okay, sorry, I hear some noise.
Yeah, Antônio, can you ligar o áudio do Frederick?
Quem é a pessoa?
Okay, thanks.
Okay,
So,
sorry about that.
No, no problem, no problem. Right, the silicon photomultipliers are not perfect, but they have a gain that depends on time. And so we use a laser system to flash laser pulses into each crystal. And we see that the, that the response to the laser converges towards flat, right, towards a uniform response, but that at early times we have to make a correction. We have to boost the value from the measurement in order to equalize it. So we use the laser pulses to correct the observed energies. This is a picture of the setup that fans out the lasers into many different beams to go into every single one of those many crystals. So our data looks like this, with the muons decaying with an oscillation modulating it. And by eye, it seems to fit a very simple 5-parameter model with an exponential decay and a cosine modulation. But if we look at the residuals following the fit, we see that there are extra peaks. There's this peak at the coherent betatron oscillation frequency. So we have to put the coherent betatron oscillations into the fit in order to get an acceptable fit to our data. So this is after including the coherent betatron oscillation terms. We get a very good chi-squared in the fit. So what are coherent betatron oscillations? Again, I have an animation of that to share. So you can see that if we look at where the muons are, because of the focusing, you know, they're always being pushed back towards the center. And so this is the profile of the beam. As you see, it goes in and out radially. Because we did not, let's see, let me go back. Yeah, it goes in and out radially, and it also gets wider and narrower. So you can see that oscillation in both the position and the width of the beam. And so we did not kick hard enough. We had a less than ideal kicker voltage in our first run. We've improved it since then. So that's why the coherent betatron oscillations were so large, because we only filled part of the accepted phase space of the storage ring. So we have increased it in more recent data sets. We had many independent analyzers that used different variations on the analysis method and got very similar results. So they all agree with each other. This Q method is a very different technique that uses a partially independent part of the data, a lot more of the energy spectrum than the others use. So that's why it's a little bit different, but these all agree statistically very well. Before we unblinded the results, so we did all of our analysis blind. We didn't let ourselves look at the physics output yet. Before we unblinded, we checked that all of these independent analyses agreed, and they did, before we moved on to looking at the physics. I should say, by the way, that visualization of where the particles are, that came from these straw tube tracking detectors that are located off to the side that can track positrons back for a subset of the positrons to the positions where the muon decayed. So we have these straw trackers at 2 locations in the ring, 90 degrees apart from each other. And so we use them to observe the coherent betatron oscillations and also to observe where the muons are so that we know how to properly weight the magnetic field. So this is the distribution of muons that we measured. This is where, on average, they were within the storage aperture. There are collimators in the ring that limit the muons to this aperture of 45 millimeter radius. Here is a map showing how uniform the magnetic field is over that over that aperture. So it's this is in parts per million. So you can see that it varies by less than plus or minus a part per million over that whole circle. And then we weighted this field map by the muon distribution to get the average magnetic field experienced by the muons. And we put that together. So, you know, the muon spin precession frequency and the proton spin precession frequency weighted by the muon distribution are the main elements of the calculation that we did. We had to include a number of corrections from beam dynamics effects, as well as corrections for transient magnetic fields produced by the quadrupoles and the kickers. So after those corrections, that gave us our final result. But it was, you know, mainly omega A and omega P, and everything else in here is a small correction. So there's a correction from the pitch, which is to say the fact that there's a beta.b term. So the muon spin it has a small component that's parallel to the magnetic field. The simple calculation assumes that it doesn't, that it's purely perpendicular to the magnetic field. And yeah, we also assume in the simple version that there's no contribution from the electric field because this is 0, but some muons have a slightly different gamma, so that there's a small correction from the electric fields. So the systematic errors associated with every term in here have been studied really in considerable detail. And we have put together a table of all of our systematic uncertainties. You can see that in our first result, the statistical uncertainty is still by far largest. So yeah, the systematics are all very small compared to the statistical error so far. And in particular, the one that we need to really work on most is this 92. It's the largest systematic uncertainty. It comes from mechanical vibrations of the quadrupole plates when we pulse them. And we have ideas to improve that for our next running period. And in our previous runs, from mapping those vibrations better than we were able to for our first publication. And then also, by improving the coherent betatron oscillations, we are going to improve this phase acceptance correction. So by making the coherent betatron oscillations smaller, the 75 and the 56 here should also get smaller. Because our goal is to get both the statistical and the systematic uncertainties below 100 parts per billion. You can see with the systematics we're close but not there yet, and we need a lot more data, but we have a lot more data for the statistics. So I know that I have been talking for a long time now. I think that perhaps I should skip over some of the details of some of these systematic error evaluations, but you could ask about any that are of interest to you. And I will just say that, you know, this is the work of 190 of us from 35 institutions in 7 countries. I think it's unfortunate that we're all in the Northern Hemisphere. I wish that we did have more collaborators from the South. But this is a picture of many of us the last time that we were able to get together in person. It was in Italy. We had our last collaboration meeting, and I think we should see a picture of our collaboration here in a minute. Yes, so we met on the island of Elba, which this looks a lot like where you are to me. Beautiful like that. Our experiment was primarily supported by the U.S. Department of Energy, Office of Science, and by the National Science Foundation, but with substantial contributions from funding agencies in all of the collaborating countries. And the group that I work with at Regis is funded by the National Science Foundation. Many thanks for that. And you can see that this result that I just showed you is from run 1. So yeah, it is only about 6% of our final data set, because we intend to collect 21 times the Brookhaven experiment. You can see that we're at about 13 times the Brookhaven experiment now. We have 2 more upcoming runs. The next one will start in October of this year. We had a very successful run 4 in spite of everything with COVID-19. We were able to run the experiment and get more data than we ever had in a running period. We eventually hope to get to 140 parts per billion precision, where that's equalized between statistics and systematics. So yeah, that's, I guess, what I have to say, and I can stop there and answer other questions that you have.
All right, thank you very much. That was a very good talk, and
Thank you.
I enjoyed it all. So let's see if the students have some questions.
Very good. Thank you. See, many people are typing.
Yes, yes. So while they are typing, maybe I can ask you when the run 2 results will be published.
So summer 2022 with a question mark. So our intention is actually to combine run 2 and 3 together into our next publication. I can imagine it could be about a year from now. So yeah, it could be August, September, October, maybe of 2022. Oh, and I realize summer is actually not a good term there, is it? So right, for you, I guess this is winter of 2022.
Yes.
Sorry. Yes, so did our experiment follow the same pattern as Brookhaven's? Yes, it did. So basically, the experimental technique, the fundamental technique, is the same between the Brookhaven and the Fermilab experiments. So what are the differences? They are really in the details. So unlike the Brookhaven experiment, we were eventually able to achieve a full kick of the beam. So we're able, not in run 1, but starting in run 3, we're able to fully kick the beam so that it's centered. I think that will be a large difference. We have the tracking detectors, so we're able to get a good measurement of those coherent Betatron oscillations in a way that at Brookhaven we never had that kind of data. The calorimeters at Brookhaven were very simple compared to the calorimeters at Fermilab. So at Brookhaven, they were basically one detector. The detectors at Fermilab are segmented into many crystals. So it's almost like every detector is really 35 detectors, right? So 2 positrons can hit different parts of the detector and be detected separately. So that's one thing that really helps there. The magnetic field measurement, the magnetic field has been made much more uniform, and we have improved our methods of measuring and tracking the magnetic field. So, yes, it's the same technique, but with many refinements between Brookhaven and Fermilab. Yeah, do I feel that the community is betting on new physics? Yes, I think that is a really good question. So yes, I think that, you know, it is experiments like ours that are seeing some indirect hints of new physics that maybe give us the confidence to move forward with other parts of the global particle physics program. So, you know, to sort of justify continuing to run the LHC, right, at CERN, you have to believe that there's some chance that you're going to find something by going to higher intensities there. And so I think that, yes, the community is really betting that the discrepancy that we see, together with a few others, like the B meson decays at the LHC, like the proton charge radius when measured with electrons versus with muons, that those hints are pointing towards something beyond the standard model that we'll eventually be able to find, that will let us reconcile what we know about particle physics with what we know about astronomy. Because we know from astronomy that, that there are, that there is dark matter, and we don't know what it is. So, yes, could it, okay, I see several questions. So there are studies that include dark photons and exotic particles that could help explain it. So I know that conventional dark photon models, now there have been enough direct searches for dark photons that the simplest kind of a dark photon cannot explain the entire discrepancy. So that's because, you know, we've searched for production directly of dark photons in many kinds of experiments. For example, beam dumps at electron accelerators. And we've excluded the masses, or not masses, the couplings that would explain as large of a discrepancy as we have with dark photons alone. But there is an idea that maybe you could have something like a dark photon or a dark Z boson, right? Some new gauge boson that that might prefer muons to electrons. So could you have a dark sector that that couples not universally to the 3 generations of leptons, but preferentially to muons in a way that the standard model can't account for? Perhaps that could be a sort of dark photon or dark gauge boson model that could explain it. So I'm really excited about some experiments that are being planned to directly search for production of exotic photons or exotic gauge bosons with muon beams. So muon beam dump experiments. I think that is a very interesting direction to go to look for the new physics of G-2. So could it be new interactions like fifth forces besides new particles? And yes, it could. So could there be some interaction that we haven't observed because it only manifests itself at very, very high energy scales? And I think the answer to that is that yes, that is not excluded. Okay, so let's see. Does the laboratory measure the electron G-2 within the theoretical expected result? So our laboratory does not, but there have been many, well, not many, there have been a number of precision electron G-2 measurements that have agreed extremely well with the standard model prediction. And so that is a very precise test of quantum electrodynamics. So that is a very precise test of those diagrams that only involve photons and electrons, for example. And yeah, that's because new physics and physics contributions from heavier particles are expected to scale with the mass squared of the probe. So because the muon's mass is 220 times the electron's mass, then it's more sensitive by a factor of 220 squared to new physics. Okay, so for the tau g minus 2, there have been very preliminary limits that have been set on tau g minus 2 because the tau is very short-lived. So you observe it, for example, at the Large Hadron Collider in tracks that are very short. And so you don't have a very long path length to see the rotation of the spin over. But people have done that measurement to the extent that it's possible given that limitation of the very, very short lifetime of the tau. And yeah, and you're welcome. It's been really a pleasure to talk with you all. Thanks very much to you all for saying thank you. Aha, do we expect to achieve a 5 sigma to characterize a discovery? And so, of course, we don't know what nature has in store for us. We don't know what the true value is. We can only make better and better approximations to it as we analyze more and more of our data. But I can say that if the magnitude of the discrepancy, if the central value remains where it is, as our error bar shrinks down, then we will achieve more than 5 sigma in the difference between the experiment and the standard model. So we have the potential to have a 5 sigma discovery if that's what nature means for us to have.
In run 2 or run 3?
So I believe
the result doesn't change, right? If it's just the systematics goes down, or where should we get 5 sigma? Run 3?
So yes, in this next publication with run 2 and 3 together, there are certainly scenarios where there could be a 5 sigma discovery at that point. But of course, it depends what comes out of the box, right, when we open the box. So yeah, we do the analysis blind. We try not to have any preconceived ideas about what the result will be before we've completed the analysis. And but there is a possibility that it could be 5 sigma already with run 2 and run 3, and an even greater possibility with the additional statistics of run 4, because we're talking eventually after run 5 of getting down to 140 parts per billion, and we're now at something like 470 parts per billion. So that's shrinking the error bar down by a lot. And it's also really rolling the dice as to where the point ends up. Okay, where does my personal hunch whisper? So yeah, I mentioned the idea of some kind of muon preferring dark matter, and that's my personal hunch. That it could be that there is some kind of dark photon with non-universal couplings. That's what I want it to be, because I really am trying to get involved in some new experiments at Fermilab that look for missing momentum when we put a beam of muons onto a target. So yeah, similar experiments with electrons have not found dark matter in the missing momentum. But yeah, the experiment with muons has not been done. The reason that it's my personal hunch, I should say, is that all of the discrepancies with the standard model somehow have muons in them. And, yeah, that really, to me, hints at non-universal couplings. Okay, do I think the results can elucidate the characteristics of a new particle? So I think only in combination with the many other precision measurements that are being done. So, we measure the shadow of the new particle as light shines onto it from one direction, but there are other precision measurements that search for, for rare decays of muons, or to muon to electron conversion, other kinds of rare processes that would violate the standard model. those are shining lights onto the new physics from other directions. If we measure the shadows of the new physics from many different directions, then I think we can elucidate the characteristics of the new particle in that way by combining all of the indirect hints. Also, for example, looking at measurements of electric dipole moments of fundamental particles, which should be 0 in the standard model, but where we would find a non-zero value from couplings to possible new physics. I should say the only place that I've seen, the only model that I've seen where we might have in our own data a signature of a new particle would be if the muons are interacting with a sort of static axion-like dark matter field that covers the detector and covers the experiment. So that would lead to a time dependence in the muon's precession frequency. So if we saw that the muon precession frequency was not stable versus time, but that the oscillation frequency was itself oscillating, that is a way that we have the potential to look for axion-like dark matter in our experiment. And we are going to do that analysis eventually.
Well, can I ask you one more question?
Sure, please.
It would be nice to know what did you do in the Brookhaven and what did you do in the new experiment at Fermilab, if you could tell us. And you were one of the 11 people that work in both, right? So we are very, very lucky to have you here.
Oh, thank you very much. Yeah, so at Brookhaven, as a graduate student, I was one of the people who did an omega A analysis primarily. So that is to say, taking the wiggle plot, the muon decay plot with the spin precession oscillation, and fitting it to determine a value for the muon spin precession frequency. So to get to that point, I wrote one of the reconstruction software programs that reconstructed the energies and times of the positrons and followed it through from that point to do the fitting and get the omega A.
So you were at the very heart of the result, right?
I guess I was. As a graduate student, you have time to do those things. So, as a faculty member at a small university where teaching is my primary job, I've had a much smaller part in this experiment mostly. I've worked on some detectors that we call the fiber harps. So they are detectors that we can insert that have scintillating fibers on them that produce light in response to the muons passing through. And we can measure directly the radial profile of the muons. So there's sort of a cross-check of the tracking detectors that I showed you. The tracking detectors see the positrons and have to extrapolate back to where the muon decayed. So the fiber harps are a diagnostic mechanism that we can use to directly measure the muon profile for comparison. So our group sort of made those work, and we've analyzed the data from those detectors. That didn't make it into this result that you saw. I think we'll have a future publication on the details of the beam dynamics that we're working on, and some data from the fiber harps will be in that paper. Also, our group has done the data quality control for the data so far. So, the experiment wasn't all working well all the time. Sometimes those electrostatic quadrupoles spark. Sometimes the kicker wasn't kicking at full strength, right? So we had to pick out the parts of the data set that had all of the components of the experiment working in their nominal way, and only include those parts in the final data. And so that's something that we really led at Regis, was the data quality control.
Okay, great. Thank you very much. I guess that's a good point for us to stop and finish the YouTube streaming. And let's thank Fred again. And then all the students have to fill some form with Antônio. So, Antônio, dá para desligar o YouTube? Acho que a gente está terminando por aqui. E o pessoal já vai agradecendo e indo embora.
Yeah, and I would thank you all again very much for the invitation. I'm very glad to have had a chance to talk with you, and I will look forward to meeting many of you all in person someday, somewhere, I hope.
Yeah, sure. Yeah, maybe. Here in Brazil, we still vaccinating people, so we are a bit behind our schedule. So, but perhaps next year things will be more normal, you know.
I certainly hope so. You know, yeah, here we have the advantage of having the vaccines available, and we just need to convince people to take them, because that certainly is the way out of this situation that we're in.
Yes. Well, I saw some news that people can get prizes and money or beer or anything if they go to vaccinate, right?
We'll try anything, right? Right. All I got was a Band-Aid